You're an astronomer in January of 2024, and you've just spent 10 hours pointing the most expensive telescope ever built at a single faint smudge of light. When the data finally resolves, the number on your screen doesn't match anything your model said was possible. Not a glitch, not a calibration error. A galaxy, fully formed, sitting less than 300 million years after the birth of the universe, when nothing that mature should exist yet. That's not physics breaking. That's physics, telling us our timeline was wrong. And as you're about to see, that single galaxy turned out to be the first thread in a pattern that's kept getting stranger every year since. Quick channel intro if you're new here, we take the biggest space headlines and check them against the actual research behind them, so you get the real story instead of the clickbait version. If that's useful to you, the subscribe button is right there. Here's the background you need first, and it starts with what this telescope actually is and why it was built the way it was. The James Webb Space Telescope launched on December 25th of 2021 and began full science operations in the summer of 2022, built specifically to see farther back in cosmic time than any instrument before it. It orbits not Earth, but the Sun, holding a stable position at a gravitational balance point known as the second Lagrange point, roughly 1 million miles from Earth, far enough out that it can keep its sensitive instruments permanently shielded from the sun's heat behind a tennis court-sized sunshield. Its mirror spans 6.5 meters across, made of 18 gold-coated beryllium hexagons, giving it more than 6 times the light-collecting area of Hubble's 2.4-meter mirror. Just as important as the size is the wavelength range. Webb is built to see in infrared light from about 0.6 microns out to 28.5 microns, and that matters for a very specific reason. As the universe expands, light from the most distant galaxies gets stretched into longer, redder wavelengths, a process called cosmological redshift. Push an object far enough away, and its light shifts entirely out of what the human eye, or even Hubble's main instruments, can see and into the infrared. Webb was purpose-built to catch that light, and in doing so, catch galaxies that existed when the universe was still in its infancy. Standard cosmology gives astronomers a fairly specific prediction for what that infancy should look like. Under the widely accepted lambda cold dark matter model, often just called lambda CDM, the universe needed real time to build anything substantial. In the earliest moments after the Big Bang, the universe was an extremely hot, dense soup of particles far too energetic for atoms to even form. Only after it cooled enough, roughly 380,000 years in, could electrons and protons combine into neutral hydrogen, releasing the faint afterglow astronomers now call the cosmic microwave background. From that point, gravity slowly pulled slightly denser pockets of gas and invisible dark matter together. Gas had to cool and collapse under that gravity. The first stars had to ignite, likely massive, short-lived, and made almost entirely of hydrogen and helium since heavier elements like carbon and oxygen didn't exist yet. Those stars had to live, fuse heavier elements in their cores, and die, seeding the next generation with the raw materials for more complex structures. Galaxies had to slowly assemble from smaller pieces, merging together over hundreds of millions of years, growing step by step rather than appearing fully formed. Before Webb ever launched, most researchers expected that hunting for bright, well-developed galaxies from the first few hundred million years after the Big Bang would be extraordinarily difficult, and that anything found there would be small, faint, and rare, a handful of dim smudges requiring dozens of hours of observing time just to confirm they were real. That expectation didn't survive first contact with real data. The first major jolt came within Webb's very first year of operations. Deep field surveys like the JWST Advanced Deep Extragalactic Survey, known as JADES, started turning up dozens of galaxy candidates at extreme redshifts, distances so great that confirming them required serious spectroscopic follow-up, not just a photo. Photometric estimates, meaning distance guesses based purely on color and brightness across different filters, can hint at how far away something might be, but they're not proof. Confirming a genuine record requires spreading that light out into a full spectrum and measuring specific, well-understood features in it, which takes far more telescope time. In January of 2024, a team pointed Webb's near-infrared spectrograph at one particularly promising candidate and observed it for almost 10 hours straight. When they processed the resulting spectrum, the redshift came back at 14.32, corresponding to a time less than 300 million years after the Big Bang. That object, now cataloged as JADES-GS-z14-0, instantly became the most distant confirmed galaxy ever recorded, shattering the previous spectroscopic record of redshift 13.2. But the distance wasn't even the most important part. The galaxy measured over 1,600 light-years across and showed strong ionized gas emission from hydrogen and oxygen, meaning it was already full of young, actively forming stars, not some dim, barely assembled fragment. Follow-up observations using the Atacama Large Millimeter Array later detected ionized oxygen within the galaxy as well, the most distant detection of that element on record, evidence that at least one previous generation of stars had already lived, fused heavier elements, and died to seed it, all within less than 300 million years of cosmic time. Researchers on the team describe being caught off guard by just how luminous and structured something this early in cosmic history turned out to be. Then, in the spring of 2025, Webb broke its own record again. A team led by astronomer Rohan Naidu at MIT identified a galaxy designated MoM-z14, confirmed at a redshift of 14.44, pushing the observational frontier back to a mere 280 million years after the Big Bang, even earlier than JADES-GS-z14-0. The team hadn't gone looking for a new record on purpose. They'd been combing through existing Webb images for overlooked candidates worth a closer look, spotted the object as peculiar, and turned the telescope toward it directly in April of 2025 to measure its spectrum properly. The study, later peer-reviewed and published in the Open Journal of Astrophysics in January of 2026, described the galaxy as brighter, denser, and more chemically rich than models had prepared anyone to expect. Naidu put it plainly in NASA's own announcement, saying that with Webb, astronomers are seeing farther than humans ever have before, and that what they're finding looks nothing like what was predicted. That's not a throwaway line. It's an admission from the person who found it that the standard playbook for early galaxy formation is missing something. Co-author Yi-Jia Lee, a graduate student on the project, added that the pace of discovery itself is part of the story, that Webb keeps revealing the early universe in ways nobody anticipated, and showing researchers how much is still left to figure out. The pattern kept escalating from there. By 2025 and into 2026, JADES and other deep survey programs had cataloged thousands of galaxies at high redshift, enough to build a real statistical picture rather than just a handful of outliers. That larger sample let researchers measure what's called the luminosity function, essentially a census of how many galaxies exist at each brightness level at a given point in cosmic history. Building that census matters because a single unusually bright galaxy could always be dismissed as a fluke, a rare cosmic accident. A whole population behaving the same way is much harder to explain away. The result held up under scrutiny. The bright end of that function, at redshifts beyond 10, came in significantly higher than pre-Webb models predicted, in some analyses by roughly 2 orders of magnitude, meaning there are simply more very bright, very massive early galaxies than standard theory allows for the amount of time available since the Big Bang. This wasn't one strange object anymore. It was a population, showing up consistently across independent survey fields observed by different teams using different instrument configurations, which is exactly the kind of cross-confirmation that rules out a single instrument glitch or one team's calibration mistake. June of 2026 added a completely different kind of evidence, this time not about a single galaxy, but about how mass clumps together on a much larger scale. A team led by researchers at Caltech's IPAC Center using Webb confirmed that a galaxy cluster called XLSSC-122, sitting more than 10 billion light-years away, is the most distant known example of strong gravitational lensing from a galaxy cluster, meaning its gravity is powerful enough to visibly bend and distort the light of galaxies behind it into stretched, arc-shaped images. Gravitational lensing itself isn't new or exotic. Einstein predicted the basic effect over a century ago, and astronomers have used it routinely for decades. What made XLSSC-122 remarkable was that Hubble had already looked at this same cluster and found no clear lensing arcs at all because the light from those distant background galaxies had been stretched into infrared wavelengths that sit largely outside Hubble's sensitivity range. Webb's near-infrared camera, observing through 4 separate filters, picked up exactly what Hubble had missed. The results, based on 3 separate peer-reviewed papers presented at the American Astronomical Society's 248th meeting on June 17th of 2026, went further than just confirming the lensing effect. Using 3 independent methods, strong lensing, weak lensing, and the pattern of light scattered between galaxies in the cluster, the team measured how tightly the cluster's dark matter is packed at its core. The concentration came out at 6.3, plus or minus 0.5, which sits outside the range predicted by every standard lambda CDM simulation for a cluster. This young, a discrepancy researchers calculated would occur by pure chance less than 0.1% of the time if the standard model were fully correct on its own. Under that standard model, dark matter halos at this particular era in cosmic history, roughly 10 billion years ago during a period researchers call cosmic noon, are supposed to still be dynamically young and comparatively loosely packed, still in the process of settling. XLSSC-122's core looked more like a fully mature present-day cluster than a young one still finding its shape. Team lead Kyle Finner was careful to frame this precisely, noting that one cluster isn't enough to rewrite cosmology, but that it tightens a specific quantitative constraint the standard model now has to explain. Barely a month later, in early July of 2026, a separate team led by Xiaohan Wang at Tsinghua University added another layer. Using Webb alongside Hubble, they identified what may be the most distant barred spiral galaxy ever found, a system cataloged as M-149 BSG-z5, dating to less than 1.2 billion years after the Big Bang, at a measured redshift of 5.102. A stellar bar is an elongated rotating structure of stars that stretches across a galaxy's center, funneling gas inward and helping build a dense galactic core over time, functioning essentially like a mechanical feed system for the black hole and central bulge. Finding one this early matters because bars are generally considered a sign of a settled, dynamically mature disk galaxy, a structure that requires an already organized rotating disk of stars and gas to even form in the first place. That's not something the standard step-by-step assembly picture expected to see this quickly after a galaxy first came together. Using a technique called isophotal analysis, which tracks how a galaxy's brightness contours change shape as you move outward from its center, the team confirmed the bar structure and even identified spiral arms alongside it, along with a possible companion galaxy sitting roughly 70,000 light-years away. Close enough that gravitational interaction between the two systems can't be ruled out as part of what triggered the bar's formation. Put together with the earlier findings, the picture that's emerged by mid-2026 isn't just that individual galaxies formed early. It's that some of them organized into recognizable, orderly structures far faster than the standard model's step-by-step assembly process was ever built to explain. So here's the part that actually matters to you, stated as precisely as the evidence allows. This is not physics being broken. The laws governing gravity, light, and particle behavior that Webb's data relies on to even function are the same laws they've always been, confirmed continuously by every measurement the telescope makes, including the very redshift calculations used to determine these distances in the first place. What's being challenged is a specific, testable model of how cosmic structure assembled over time. The Lambda CDM framework's predictions about the pace of galaxy formation in the first several hundred million years. That distinction matters because it tells you what would actually have to change if these results hold up under further scrutiny. It wouldn't mean gravity works differently or that relativity is wrong. It would mean astronomers need to revise their understanding of how efficiently the early universe converted gas into stars, how quickly the first galaxies merged and organized, or potentially some other input into the model that hasn't been fully identified yet. Several explanations are currently being tested against the data, including the possibility that early stellar populations converted gas into light more efficiently than assumed, since the very first generations of stars were likely more massive and burned hotter than stars forming today. Another possibility is that feedback processes, meaning the way radiation and stellar winds from newborn stars normally push back against and slow down further star formation, behaved differently in the metal-poor environment of the early universe, allowing star formation to proceed in short, intense bursts rather than the smoother, self-regulating pace seen in galaxies today. A third line of explanation suggests some of these galaxies are appearing brighter than their actual stellar mass would justify, because intense, short-lived bursts of star formation can temporarily make a galaxy look far more luminous than its underlying mass would predict under standard assumptions before settling back down. Most cosmologists remain cautious about declaring the standard model broken, since better modeling of how starlight translates into observed brightness or subtle selection effects in which galaxies happen to get chosen for expensive spectroscopic follow-up could still account for some of the gap without requiring any fundamental revision at all. What isn't in dispute is that Webb has forced a genuinely productive rethink of when and how the first massive galaxies came together, and that rethink is driving some of the most active theoretical work happening in cosmology right now, filling astrophysics journals with competing models trying to close the gap between prediction and observation. This matters beyond academic curiosity, because the Lambda CDM model isn't just used to describe galaxy formation, it's the same broad framework underpinning predictions about dark matter distribution, the large-scale structure of the cosmic web, and even estimates of the universe's expansion rate. A model that needs adjusting in one area invites careful and warranted scrutiny of its assumptions elsewhere too. That's exactly why findings like XLSSC-122's overly concentrated dark matter core carry weight well beyond one unusual cluster. They represent an independent line of evidence pointing in the same general direction as the early bright galaxy problem, using completely different physics and completely different measurement techniques to arrive there. As of the summer of 2026, the research hasn't slowed down at all. The JADES survey and similar deep field programs are continuing to expand their catalogs, adding statistical weight to the early galaxy population every few months, rather than relying on isolated record breakers. The XLSSC-122 results from June are already prompting follow-up proposals to search for more early overconcentrated galaxy clusters using X-ray and radio surveys to find candidates, since Webb's narrow field of view means it can't simply scan the whole sky looking for them on its own. It needs other instruments to point it toward promising targets first. One particularly promising method involves the Sunyaev-Zeldovich effect, a subtle distortion that massive galaxy clusters imprint on the faint microwave afterglow left over from the Big Bang itself, essentially leaving a detectable fingerprint that tells radio astronomers roughly where to look before Webb ever gets involved. Astronomers are also pushing to understand which galaxies actually drove the process called reionization, the period when the first generation of stars and galaxies flooded the universe with enough ultraviolet light to strip electrons from the primordial hydrogen fog that filled space, transforming the cosmos from largely opaque to transparent. Early results from spectroscopic surveys suggest both large numbers of faint, ordinary galaxies and a smaller number of unusually bright ones contributed to that process, with the bright ones playing a larger role in some regions than earlier models assumed, meaning the same population of surprisingly luminous early galaxies, causing headaches for the lambda CDM timeline, might also be rewriting how astronomers think the universe became transparent in the first place. That's a second related mystery riding on the coattails of the first one, and Webb's ongoing spectroscopic campaigns are gathering the data needed to eventually separate the two contributions cleanly. Woven through all of this is another puzzle that's been building in parallel, one Webb's own deep surveys turned up almost by accident. Scattered across the same deep field images used to find these record-breaking galaxies, astronomers kept spotting a distinct population of small, extremely red compact objects that didn't behave like ordinary early galaxies at all. Researchers nickname them little red dots, and the debate over what they actually are has become one of the more contentious threads in this whole story. Some studies argue they're dominated by rapidly growing supermassive black holes, essentially compact, obscured versions of the bright cores seen around black holes in the modern universe, just packed into a much smaller, younger package. Other analyses suggest at least some of them are extremely dense clusters of stars, rather than black hole activity at all, with follow-up spectroscopy needed case by case to tell the difference. Either explanation adds another wrinkle to the standard timeline, because both a population of unexpectedly early, rapidly growing black holes and a population of unexpectedly dense, compact star clusters point toward the same broader theme running through everything else covered here, that whatever process built structure in the first few 100 million years after the Big Bang worked faster and more efficiently than the standard model currently accounts for. If you've stuck with the numbers this far, here's the short version of everything above before we move into what's still unsettled. 4 independent findings, spanning individual record-breaking galaxies, a statistically robust population of unusually bright early systems, an overconcentrated galaxy cluster, and a fully structured barred spiral, have each landed on the same side of the same argument, that something in the standard timeline for how cosmic structure assembled needs to be revised. Add the little red dots puzzle on top, and it's closer to 5 separate, independently gathered threads, all pointing the same direction. That's the actual headline. Not broken physics, a broken assumption about pacing. What's still genuinely unresolved is worth stating clearly. Nobody has a single settled explanation yet for why so many early galaxies are this bright, this massive, and in some cases, this structurally organized, this early. The leading candidate explanations aren't mutually exclusive, and it's entirely possible the real answer involves a combination of several factors working together rather than one clean fix, some mix of more efficient early star formation, altered feedback physics, and observational effects, each contributing part of the discrepancy. There's also active debate about how representative these record-setting galaxies actually are. Every deep survey has natural biases toward finding the brightest, easiest to detect objects first, so part of the ongoing work is figuring out whether typical early galaxies were mostly small and faint as originally predicted, with these luminous outliers as genuine rarities, or whether the outliers are hinting that the whole early population was more vigorous than assumed. Distinguishing between those two possibilities requires exactly the kind of large, statistically robust samples that JADES and similar programs are still in the process of building, samples large enough to average out the natural randomness in any small collection of unusual objects and reveal the true underlying trend. A handful of researchers have proposed more dramatic alternatives, including modifications to how redshift itself is interpreted, or entirely different cosmological frameworks outside standard lambda CDM. These remain minority positions within the professional astrophysics community, and the vast majority of researchers working directly with the data continue to treat this as a puzzle to be solved within the existing framework through refinements to star formation physics rather than a wholesale replacement of the model. It's worth being upfront that debates like this attract attention from outside mainstream cosmology too. including efforts to use these same anomalies to argue against the Big Bang framework entirely. Those arguments haven't gained traction among researchers actively working with Webb's data, since the same observations that reveal these puzzling early galaxies also continue to independently confirm the universe's expansion, its age, and the broader Big Bang timeline through multiple other lines of evidence, including the cosmic microwave background, and the observed abundance of light elements like hydrogen and helium that remain fully consistent with standard cosmology. The honest scientific position, shared by essentially every team involved in these discoveries, is that the framework is being stress-tested and refined, not discarded, and that distinction is the whole difference between a healthy scientific debate and a manufactured controversy. What comes next is already scheduled. Deep survey teams are continuing systematic spectroscopic follow-up on the backlog of high redshift candidates sitting in Webb's archives, meaning more confirmed record holders, or more importantly, more confirmed members of this same puzzling population are likely before the end of the year. Researchers studying XLSSC-122 have said plainly that finding tens or even hundreds of similarly concentrated early clusters would let them properly stress test the standard cosmological model rather than relying on a single striking exception. And that kind of large-scale statistical test is exactly what separates a genuine crisis in cosmology from a handful of interesting but ultimately explainable oddities. And missions still to come, including wide-field surveys designed to cover far more sky than Webb's narrow targeted view allows, are expected to locate many more candidate clusters and galaxies for Webb to then study in the kind of detail only its instruments can provide. That's the practical division of labor astronomers are now building around, wide survey telescopes finding the candidates, and Webb doing the deep, expensive follow-up work needed to confirm them with real spectroscopic certainty. There's also a deeper theoretical question hanging over all of this that researchers are actively trying to answer, not just at the level of individual galaxies, but at the level of the underlying physics of the very first stars. If early stars really did form and die faster and in greater numbers than standard models assumed, that has implications reaching beyond galaxy brightness alone, touching on how quickly heavy elements were seeded into the early universe, how quickly the first stellar mass black holes formed, and even how the earliest supermassive black holes at galaxy centers managed to grow so large so fast, a separate and related puzzle astronomers have been wrestling with since some of Webb's very first observations. None of these threads are fully untangled from each other yet, and resolving one is likely to inform the others, which is part of why this particular corner of cosmology has become such an active, fast-moving area of research barely 4 years into the mission. None of this means the universe's rulebook has been torn up. It means astronomers pointed the most capable telescope ever built at the earliest moments we can observe, and the universe answered back faster and more organized than the paperwork said it was allowed to be. Every galaxy chart drawn before 2022 assumed the deep past would look sparse and unfinished, a rough draft waiting patiently to become the cosmos we see today. Instead, the draft keeps turning out to already have sentences written in it, structure where there should only be scattered gas, bars, and spiral arms, where there should only be shapeless clumps, densely packed dark matter cores, where there should only be loose, still-forming halos. 4 separate lines of evidence now point the same direction, spanning individual record-breaking galaxies, a full statistical population of unusually bright early systems, an overconcentrated galaxy cluster, and a fully structured barred spiral, each measured with different instruments, different teams, and different techniques, yet all converging on the same basic conclusion that the standard timeline needs revising somewhere. Webb didn't shatter physics. It handed physics a stack of early drafts nobody expected to find already this far along, and cosmologists are still working out exactly what that means for the story they thought they already knew. What makes this moment genuinely rare in the history of the field is that it's happening in real time, in public, with new data points arriving every few months rather than emerging from decades of slow, incremental theoretical debate. The last time, cosmology faced a comparably open, actively contested question. This central to the standard model, it took the better part of a generation to sort out. This time, thanks to one telescope sitting nearly 1 million miles from Earth at the second Lagrange point, we get to watch the argument unfold as it happens. If you want more of these headlines actually checked against the papers behind them, rather than the version built purely to get a click, subscribing helps a lot. Let me know in the comments which of these findings surprised you most. And if you know someone who saw this title and assumed the actual laws of physics got rewritten, send this their way and set the record straight.